APCACUS BC, 413 office hours, little extra credit review for your upcoming test. So, sort of like a note sheet for some stuff, and there's a couple examples on the back, but so conversions, x equals r cosine theta, y equals r sine theta. You guys use those all the time. X squared plus y squared equals r squared. You could always draw a little picture over here to show those relationships. It's a pretty basic trig relationship. So this is your x, y coordinates, and polar is just describing the same location with an angle instead and a radius. So the relationships is if you drop this down, this is your x from here to here, this is your y from here to here. That's where the Pythagorean theorem comes in to get r x squared plus y squared equals r squared. Then use basic trig. If you have r and theta and you want to get x, well, that would be adjacent to hypotenuse. So you use cosine theta equals adjacent over hypotenuse. And then if you solve for x, you get x equals r cosine theta. And if you want to find y, you do opposite, y over hypotenuse. And that'd be sine, and solve for y, and you get y equals r sine theta. Tangent theta equals y over x. So then you could, of course, say that theta equals inverse tangent of y over x. And then you got to make sure you're in the correct coordinate. So if you have a r theta, so it's always r comma theta, radius first, then the angle, and it has to be radians. We could always add pi or take away pi from this to get an angle on the other side, then use a negative radius. So you could do that. That would give you the same location. If you wanted to convert this to xy, well, you would use this relationship right here. You say x equals 4 cosine pi over 6. And so that'd be 4 times root 3 over 2. And so that'd be 2 root 3. Then the y value would be 4 sine pi over 6. And so that would be 4 times 1/2. And that would be 2. So I have a couple problems like that on the test where you got to give me some other polar coordinates to give the same location or convert from one coordinate system to another. All right, so some of the basic shapes. A line, which is kind of rare, we don't see as a lot, would just be like a constant angle. So like sketch of that, it'd be like this, it'd just always be the same angle, and it would be every possible radius would be fair game, positive and negative. So that's how you get a line using polar. Circles, there's the basic circle that's centered at the origin, and it has a constant radius, let's say of k. So you could just say r equals k, right? The radius. And then it doesn't involve angles because it's the same radius all the time. But usually we get these other ones, like you get these ones that are kind of up here, or we get these ones that are kind of like over here. And those usually are in the form of a sine theta for the vertical ones, and it could also be down here, and a cosine theta for the horizontal ones. It could also be over there. And in these scenarios, a equals the diameter. And you only need 0 to pi to graph the whole thing. Whereas most of the other shapes need 0 to 2 pi. Cardioids take the form of a plus b sine theta, or a plus b cosine theta. Those would give you cardioids. But a has to equal b. That's the requirement. And cardioid kind of looks like that, And same thing, if it's sine, it's going to be vertical. If it's cosine, it's going to be sideways. Rose curves are going to be a sine in theta or a cosine in theta. So they have this extra number on the inside where n is greater than 1. Now, if n equals 1, that's actually one of these circles over here, which you could think of as a one-petaled rose, whatever. But in these cases, a equals the radius of the rose. And usually sketch that first. If n equals odd, then you're going to get, if n equals odd, you're going to get n petals. And then you only need 0 to pi to graph the whole thing. If n equals even, you're going to get 2 times n petals. And to graph the whole thing, you have to go 0 to 2 pi. So usually look for the tips of the petals by setting your radius equal to plus or minus the maximum radius. In general, they often have symmetry. And if it involves sine of some kind for any of these shapes, usually it's going to have y-axis symmetry, which is, so it's going to be vertical in nature, and it's going to be sort of like an even function, even though these aren't totally functions based off of rectangular coordinates. If it involves cosine, it's going to be sideways, so it's going to have like an x-axis symmetry. It's going to be the top half is going to be the same as the bottom half, like if you flip it over the x-axis. So it's kind of a bunch of basic shapes. There's some other ones, limacons with inner loops, convex limacons. Now, dy dx, which is kind of punched out by this hole right here, is equal to dy d theta over dx d theta. Because our equations are all in terms of theta, so you're going to have to first take, so we're taking the derivative first with respect to theta, or with the variable that's in, and then it's like kind of a chain rule. You got to take the derivative of theta with respect to x. Now, that's all you need to remember. There was a formula. I'm not going to, I guess I'll write it down just to help verify these shortcuts. Because x equals r cosine theta and y equals r sine theta, then we could write a special form of this with r in it generically. It's not that useful in general, and I don't want to see you use it. I'm going to cross it out right for this, but it's going to help us verify the shortcuts real quick. That I'd probably just memorize it if we're going to use them. Otherwise, just do it the long way. So the derivative of r is going to be r times derivative of sine is cosine plus r prime times sine. So it's just a product rule. Even if you're going to use this formula, it's not worth memorizing. It's easy to try. It's going to be r sine theta with a negative plus r prime cosine theta. So we're not going to memorize this, but it does kind of help show this. Like if r is 0, then these terms just go away, and you're left with these, and r primes are the same, so you just get sine over cosine, or tangent. At the pole, dy dx simplifies that. At a max radius, you're looking at the derivative equals 0 because it's going to be a critical point. So these terms are going to go away, and you're going to be left with these terms. The r's are going to cancel, and you have a cosine over a negative sine, or negative cotangent. I think the pole one is more often used, but do not use that formula in your work. I don't want to see it. Okay, horizontal tangents and vertical tangents. So horizontal tangent in general, since last year in Calc AB, is when the slope is 0. Now in this case, because dy dx equals dy d theta over dx d theta, that means the numerator must be 0. And the denominator hopefully is not 0. It can be, but it's indeterminate. So you got to do L'Hopital's rule, or maybe rely on the picture. I'm encouraging you to just rely on the picture. So anytime you have a cusp, you're going to get this situation. So you're going to have to verify which one it is. Now, vertical tangent is whenever the slope is undefined, it's infinitely steep. And that's going to happen when the denominator goes to 0, but hopefully the numerator is not 0 at the same time. It can be, but it's indeterminate and you have to figure it out. So you can be vertical and horizontal at the same time. So if it shows up on both, then you got an issue that you got to figure out. So the area, we talked about this. I mean, I could rederive this formula really quickly. Each slice was like a sector, and it had a d theta, or we could just go with theta first. It had a theta and a radius. And back in geometry, if you want to find the area of that sector, you'd say, okay, well, theta over 2 pi equals the area of the sector over the area of the whole circle, right? Which is pi r squared. So then the area of the sector is going to be theta over 2 pi times pi r squared. And you're going to get 1/2 pi r squared, you get 1/2 r squared theta. That's how you find the area of a sector back in geometry. So we're going to use that idea here. We're going to say, okay, well, this is d theta. So the area of one slice is going to be 1/2 r squared d theta. That's one slice. And if you want all the slices, you're going to integrate. Them. So usually put the 1/2 in front just because that's easier. But that is the area. So probably memorize it. I mean, the derivation was pretty simple, but I don't think you want to go through that every time. Okay, arc length. I'm not going to show the derivation of this. We just showed this recently in notes, but it comes from like a secant line on one of these slices, being the hypotenuse of the little red triangle. And it starts with this, but then we got a nice simplified version that's r squared plus drd theta squared. Now, it's not the second derivative of r, that's the first derivative squared. So that's what you want to use. Okay. You can put an r prime here if you want to. Same thing. Trig identity. So often on a lot of these problems, they kind of come up, but especially on the area problems, this double angle identity. So double angle for cosine is cosine squared minus sine squared. Other versions of it using Pythagorean trig identity, you get 2 cosine squared minus 1 or 1 minus 2 sine squared. So from this, you could solve this. You could say, well, cosine squared equals 1/2 plus 1/2 cosine 2 theta. And from this one, you can solve for sine squared, and it would be 1/2 minus 1/2 sine 2 theta. Or sorry, cosine 2 theta. So they both use cosine, double angle. The only difference is the plus and the minus. So we're going to use that. We use those a good amount of time to help us get something that we can actually integrate. So in the back, we got some examples, maybe a little practice, multiple choice problems. So it says, number 1, which of the following is not the same as the others? So as far as like polar coordinates, which one is not the same? So, I mean, you could kind of like draw a generic picture. You could say, okay, well, this is theta and this is a radius. Now, if we were at negative theta, that it depends on this angle. I mean, it could be right here and the negative angle put over here. So that one's not the same. That one's not the same as that one. Which of the following is not the same? So this one's already not the same as that. This one right here, if we subtract pi from this, that would bring you back over to here, and a negative radius would put you over there. So these two are the same. Or if you add pi to this, put you there, a negative radius puts you over there. That one's the same. Or if you subtract 2 pi, you'd end up back at the same spot with positive radius is the same. So this one is not the same. So that's a little kind of negative radius, other coterminal angle issue, which the following gives a slope of r equals f theta in the xy plane. So slope is dy dx. And so then that would be dy d theta over dx d theta. So I think that's what I'm looking for. Dy d theta over dx d theta. I know that one's kind of weird looking, but the area enclosed in this shape, well, it's probably going to be 0 to 2 pi. It's probably, well, 1. You're going to do 1/2, and it might be 0 to 2 pi of the radius squared d theta. Now, I'm not really quite sure in the shape of that, but maybe we could use symmetry. But these two are for sure out, because what you get if you square that square root, the square root goes away, right? This one's for sure out, so it's got to be one of these. So I'm thinking it's this one based off of using symmetry. 2 times 1/2 0 to pi, the square root gets squared, right? That might be a stretch, but or you could sketch the shape. I just don't. I think I did sketch it, and I got something like that. Okay, which integral gives the area that's inside this but outside this? So these are both circles, so I'd sketch it real quick. Both sideways circles, theta r, you only need to go to pi. So the first one's going to be 2, 0, 2. And the second one's going to be 1, 0, 1. So if we were to graph them together, that's the first one. And that's the second one. And it's inside the big one and outside the small one. So that would be all of this. So most likely we'd probably use, and we got to figure out these angles. These both start here and go this way, right? At theta equals 0. And then when they get to this point, they're at theta equals pi over 2. I mean, just look at the tables. So I'd probably use symmetry and say, okay, well, I'm going to just do half of the area. Now, when you do that, you got to find the bigger area and then subtract the smaller area from it. So the bigger area is going to be 0 to pi over 2 of 2 cosine theta squared d theta. And then the small one's going to be 1/2 0 to pi over 2 of cosine theta squared d theta. So, I mean, that's the first thing I would think of. And then that would give you the 2's cancel. So, I mean, go to 4 here. I don't think I need to change the squared. I don't think I need to use the trig identities to get rid of the cosine squared. Looks like a lot of these answers have cosine squared. So that would give you that. I mean, so we could simplify this a good amount without even integrating. So here we go. D. All right. Here's a problem that kind of looks kind of like a free response style problem. Set up an integral and then evaluate it to find the area bounded by the curve in the x-axis. So there's this curve here. If we were to try and make this is a weird shape, but if you plug 0 in here, you get 0 pi over 2. You're going to get a pi over 2 pi. You're going to get pi. So if you were to graph this, 0, 0, pi over 2 be like 1.6, and then be 3.14. So it's doing something like that. Anyways, that's kind of what it looks like. I mean, you could graph it in graph calculator if you want to figure out the shape of it. And we could possibly get away with this without having a graph, but it just helps. Now, if you want to find the area of it, it's going to be 1/2. We're not going to use symmetry. 0 to pi of theta plus sine 2 theta squared d theta. So I think we could have done that without a graph. If you were to try and solve by hand, you'd get stuck. So you'd have to use a calculator. So just for practice, you might try it on your calculator. And you should get 4.382. So on your calculator, I do it in regular function mode. Math 9, fnt, parentheses, or 0.5, parentheses, don't forget the 0.5, x for the thetas plus sine 2x, close, squared, comma, x, comma, 0, comma, pi. 4.382. Find theta that corresponds to the point on r equals theta what x equals -1. So there's some point right here where x equals -1, right? You want to know, well, what's the angle where that happens? What's theta? I think you probably need to use a calculator to do this. So this probably should be a graph. Yeah, this should be a graphing calculator problem. Okay, so and then that would have helped in the quick graph too. Okay, so we're gonna say, well, x equals r cosine theta, right? And so that's gonna be theta plus sine 2 theta times cosine theta, and that should equal -1. So we got to solve that. So on my calculator, I mean, you could distribute this if you want. I don't know if that's super helpful. But then I would move the 1 over here equals 0 and solve that on my calculator. I know the answer should be between 0 and pi, so that's going to help me set my limit. So I'm going to go to y equals, I'm going to put x cosine x plus sine 2x cosine x plus 1. Go to window, 0 to pi, -1 to 1. I think there should only be one answer. If I get more than one, I should be worried. So there it is. Definitely second quadrant, which my picture shows me. Second calc, 0. It's between 2 and 3. Guess 2.5. It is 2.380. There you go. All right. What intervals is drd theta positive? Now, visually, when is the graph getting bigger? I'd say, well, looks like it's getting bigger for that chunk, and then, I don't know, maybe somewhere around here or something. Looks like it's kind of getting close to the interval. But what we should do is we should just graph. We should find drd theta. It should be 1 plus 2 cosine 2 theta. And say, well, where is that bigger than 0? Now, I can probably solve that by hand, actually. Do like a line check. The easiest thing is to put this in your calculator. And window is 0 to pi. I don't know, x min, so we could do zoom fit. It takes a little extra longer. So it's going to graph that drd theta, and we say, well, it's positive there, it's negative there, it's positive here. So we're trying to find those points right there. So you do a second calc 0. You say, well, looks like there's one between 0.5 and 1.5. I'm going to guess 1. And it is 1.047196. And then I'm going to do the other one so I can calculate 0. Looks like there's 1 around 2, so maybe like 1.5 to 2.5. Guess 2.1. 2.0943951. So I could say the answer is, interval answer. I could say, well, from 0 to 1.047 parenthesis union parenthesis 2.094 to pi bracket. So that'd be your answer. If you do it by hand, you would just solve that trig inequality. So you'd say, okay, well, let's set it equals 0. Say cosine 2 theta equals -1/2. Reference angle is pi over 3. Quadrants 2 and 3. 2 theta equals 2 pi over 3 plus 2 pi k. Theta equals pi over 3 plus pi k. 2 theta equals 4 pi over 3 plus 2 pi k. Theta equals 2 pi over 3 plus pi k. So line check, going from 0 to pi. So we do pi over 3 and 2 pi over 3. Open dots because it's greater than, not equal to. We test a value. So this is drd theta, by the way. Test 0 would be great. Plug 0 in here. It is positive, true, false, true. And this answer is the same as the answer we got from our calculator, but with nice exact values. So that's fine. Either way, I'd probably use my calculator. It'd be quicker and more reliable. Okay, on what value of theta between pi over 2 is the curve farthest from the origin? So farthest from the origin means we're looking for max absolute value of r. We should do EVT. We got endpoints. We need critical points. So that'd be where drd theta, which equals 1 plus 2 cosine 2 theta equals 0 undefined. Now we just found those points on the last problem, right? That's what all that work was for. So we can say, all right, well, theta equals pi over 3 and 2 pi over 3. Those are your critical points on the interval between the endpoints. Or you can use those decimals. You could use this method of to find those critical points. Then we do a quick chart. 0, pi over 3, 2 pi over 3, pi. Plug them into R, the original R equation. Now from the picture, I think max R is over here at pi. So let's see if that verifies that. 0, pi over 3, sine of 2 pi over 3 is going to be root 3 over 2. And then 2 pi over 3, plug that in, you get 4 pi over 3, that's 3 quadrants, so that's going to be minus root 3 over 2. And then you plug pi and get pi. So this is about 3.14. You could use your calculator. Oops, we're only doing pi. It's pi over 2. Pi over 2. So if you do pi over 2, you get pi over 2, just pi over 2. Now, on your calculator, you could figure out what these decimals are real quick. Pi over 3 plus root 3 over 2. That's about 1.913. And then we could do pi over 2, and that's about 1.570. So this is your max. And in the first quadrant, it does look like the max is somewhere, isn't at the edges between 0 and pi over 2. So we could say the curve is, and we could have done absolute value here. They all came out positive, so that's right. Curve is farthest from the origin when r equals pi over 3 plus root 3 over 2 at theta equals pi over 3 by extreme value theorem. By checking endpoints and quarter points. There you go. Find the length of the curve. So the length of the curve is the integral of r squared plus drd theta squared from 0 to pi. So that's going to be r is theta plus sine 2 theta. And drd theta, we already found a couple times, is 1 plus 2 cosine 2 theta. So that's your setup. And I'm just going to put that in our calculator. So I wouldn't be in polar mode for this. I would just do math 9, put x's for all those. So it's going to be square root, parentheses, x plus sine 2x, close the sign, close parentheses, squared, plus, parentheses, 1 plus 2 cosine 2x, close the cosine, close parentheses, squared, close parentheses on square root, comma x, comma 0, comma pi. Enter. 7.169 or 7.170 if you want to round. So there you go. I have another free response problem that I'm going to do in a separate video. So